Okay. Today I will talk about real-world applications of calculus. We will talk about three parts. Part one is the applications of the derivatives in economics, and part two is exploring the virtual method for volumes of revolution. Part three is understanding moments and the center of mass. Okay, so I will begin by discussing the applications of the derivatives in economics. The derivatives in simple terms help us understand the rate at which one quantity changes with respect to another. This concept plays a crucial role in analyzing and optimizing various economy functions. Let us explore six key functions where derivatives are applied. Cost function, average cost function, revenue function, average revenue function, profit function, and average profit functions. The first one, cost function. The cost function represents the total cost of producing a certain number of goods. Derivatives help us calculate the marginal cost, which tells us how much the cost will increase if we produce one more unit. For example, if the cost function is C of x, the marginal cost is the derivative of C with respect to x. This information is vital for manufacturers to determine production efficiency. The second one is average cost function. The average cost function calculates the cost per unit of production, expressed as AC of x equals to C of x divided by x. The derivative of this function indicates whether the average cost is increasing or decreasing as production scales up. The third one is revenue functions. The revenue functions R of x shows the total income generated from selling X units of goods. This is the derivative called marginal revenue, tells us the additional revenue generated by selling one more unit. Businesses use this to determine pricing strategies. The fourth one is average revenue functions. The average revenue functions AR of x equals to R of x divided by x helps assess the revenue per unit. The derivative of this function aids in understanding how revenue per unit changes with output. The fifth one is profit function. The profit function is defined as profit of x equal to revenue of x minus cost of x. Its derivatives identifies the production level where profits are maximized. This is often referred to as the critical point. The sixth one is average profit function. Similarly, the average profit function average profit of x equals to profit of x divided by x. This used to calculate the profit per unit. The derivatives reveal trends in average profitability as production changes. And now let us look at 3 examples to illustrate this concept. First example is marginal cost and efficiency. Suppose the cost function for producing x units is C of x equals 5 times x squared plus 10 times x plus 50. The marginal cost is the derivative of c with respect to x, which equals to 10 times x plus 10. For example, when x equals 5, the marginal cost is 10 times 5 plus 10, which equals to 60. This means producing one more unit at this level increases costs by 60. The second one is maximizing profit. Consider the revenue function Rx equal 100 times x minus x squared, and the cost function C of x equal to 20 times x plus 50. The profit function is defined as profit of x equals R of x minus C of x, which simplifies to 80 times x minus x squared minus 50. Taking the derivative of the profit function gives 80 minus 2 times x. Setting this equal to 0 and solving for x, we find x equal to 40. This means producing 40 units maximizes profit. The third example is analyzing average cost. If total cost function is C of x equals 50 times plus 200, the average cost function is average cost of x equals 50 plus 200 divided by x. Taking the derivative of average cost with respect to x gives negative 200 divided by x squared. This indicates that the average cost decreases as x increases. Part 2, in this part, I will explain the washer method, which is used to calculate the volume of a solid of revolution. This method is especially helpful when the solid has a hollow region, like a donut or a hollow cylinder. Okay. The concept of the washer method. The washer method slices the solid into thin discs or washers. Each washer has an outer radius and an inner radius. The total volume is found by summing up the volume of this washer using integration. The formula is written as V equal to pi times the integral from A to B of outer R of x squared minus inner R of x squared with respect to x. And here, the outer radius is the distance from the axis of rotation to the outer edge, and the inner radius is the distance from the axis of rotation to the inner edge. A and B are the bonds of integration. This formula subtracts the volume of the inner part from the volume of the outer part to get the total volume. Let's look at example. Let us consider a special example. Suppose we want to calculate the volume of a solid formed by revolving the region bound by y equal to x squared and y equal to 4 around the x-axis. First, we will identify the radius. The outer radius is equal to 4, and inner radius is x squared. The second is set the bounds. The region is bounded by x equal to -2 and x equal to 2. Then we will apply the formula. First using the Washer method formula. And then we will simplify the terms inside the integral. And then we will evaluate the integrate as this one. And the first term and the second term is equal to this and this. Then substituting back, we will get v equal to pi times 46 minus 0, which equals to 64 pi times pi. Thus, the volume of the hollow cylinder is 64 pi cubic units. And in part 3, which is understanding moments and the center of mass. In this part, I will explain the moments and the center of mass. These are important ideas in physics and engineering that help us understand how mass is distributed and locate the balance points of an object. First, we talk about moments. A moment measures the turning effect of a force around a point. For a system of particles, the moment about the x-axis is found by summing the product of each particle's mass and its distance from the x-axis. The formula for the moment about the x-axis is written as moment about the x-axis equals to the integral from a to b by y times the density function of x and y with respect to x. Similarly, in here, moment about the x-axis is the and y is the vertical distance of each particle from the x-axis. And this one is the mass density function. And A and B are the bounds of the region. Similarly, the moment about the y-axis is moment about the y-axis equal to the integral from a to b of x times the density function of x and y with respect to x. This measures the turning effect around the y-axis. And then we will talk about the center of mass. The center of mass is the balance point of an object. Its coordinates are found using the moment. The x coordinate is moment about the y-axis divided by the total mass, and the y coordinate is moment about y-axis divided by the total mass. And the total mass is the integral of density function over a region. Let's look about an example. Let's consider a thin rod of length 4 units. For units lying along the x-axis with a mass density function rho of x equal to 2 plus x. First, calculate the total mass. The total mass is integral from 0 to 4 of 2 plus x with respect to x. This equal to 16. And the next, we find the moment about the origin, which is the y-axis. The moment about the y-axis is integral from 0 to 4 of x times 2 plus x respect to x. After solving, this equals 112 divided by 3. And finally, we will compute the center of mass. The x coordinate of the center of mass is moment about the y-axis divided by the total mass, which equals to 7 divided by 3. Since the rod is symmetric, the y-coordinate of the center of mass is 0. And that's all.